Hi everyone, I'm Fuad, and today I'm happy to present you part of our work on detection, measurement, and lawfulness of cookie respawning with browser fingerprinting. We define cookie respawning with browser fingerprinting as the combination of both stateful and stateless tracking techniques. So before presenting our work, let me start with a small introduction on how stateful and stateless tracking techniques work. Stateful tracking relies on the usage of browser storages such as cookies. To better understand how it works, let's consider a user browsing the web. The user is visiting bbc.com that includes content from DoubleClick. In order to fetch the content, the browser automatically sends a request to DoubleClick. Using the request response, DoubleClick will set a cookie on the user's browser with as value the identifier 1234. Now the user visits a different website, let's say newyorktimes.com, that includes content from the same domain, DoubleClick. Again, a request is sent to DoubleClick to fetch the content, and along with the request, the browser automatically attaches the cookie ID equal 1234. Using this identifier, DoubleClick can recognize the user and recreate her browsing history. Stateless tracking, or what is commonly known as fingerprinting, allows tracking using browser and machine features. This time, let's assume that New York Times include a fingerprinting script from DoubleClick. The script accesses a number of users' browser and machine features such as time zone and resolution, then send back the data to DoubleClick. Along with the request, DoubleClick receives additional features referred to as passive features that are automatically attached to the request, such as user agent. Using this information, DoubleClick can generate a fingerprint, in that example AFP456, associated to the user or group of users, and then similarly to what we have seen in stateful tracking, use this identifier to recreate the user's browsing history. For simplicity, in the following, we refer to this process of fingerprinting as this arrow. To sum up, we've seen that we have two big categories of tracking. Stateful, that relies on the user's browser storages, such as cookie storage. It's a stable way to track users, however, it requires storages. Stateless tracking that relies on the user's browser and machine features. It does not require any storage, but it's not stable over time. Several studies measured the prevalence of stateful and stateless tracking techniques separately. However, to the best of our knowledge, none of these works studied the combination of both tracking techniques. In this work, we study how trackers can combine the two tracking techniques and take advantage of the best of the two worlds. As you might know, today we're moving toward the application of third-party cookies. In this study, we show how cookie respawning with browser fingerprinting can overcome the duplication of third-party cookies and still ensure persistent tracking. Finally, we study the privacy and legal application of this tracking behavior with the help of a legal scholar. So how cookie respawning with browser fingerprinting works? Let's go back to our example. The user is visiting bbc.com that have the fingerprinting script from DoubleClick. A request is sent to DoubleClick along with the browser and machine features. DoubleClick generates the fingerprint, FP456, and then store it on a matching table with the corresponding identifier, let's say 1234. DoubleClick will then send back a response and set a cookie on the user's browser with as value 1234. Now let's say that the user cleans her browser, including cookie storages, and revisit the bbc.com website that still include the script from DoubleClick. A request once again is sent to DoubleClick that will generate the same fingerprint, FP456, check the matching table, extract the corresponding identifier, 1234, and sets back a cookie with the same ID 1234 on the user's browser storage. Now, how to study cookie respawning with browser fingerprinting in the web? In the following, I will summarize our methodology. For this work, we studied Alexa top 30K websites. For every website, we make a first call that we refer to as initial call. Then we clean all browser storages, including cookie storage, open a new browser instance, and perform a second call that we refer to as reappearance call. Using these two first calls, we detect cookies that are recreated with the same value after we clean the browser storages. To discard cookies that appear systematically with the same value in every call, we perform a third call from a different machine that we refer to as user-specific call. And so as a result of this first step, we collected the cookies that reappear with the same value when we revisit the same website on the same machine, and are additionally user-specific, meaning that the value of these cookies changed when we called from a different machine. We refer to this set of cookies as respond user-specific cookies. Next, we analyze the dependency between the response cookie and the studied fingerprinting features. For simplicity, let's take the example of the cookie ID for 1234 that appears on bbc.com. Let's say that the question we want to answer is whether the cookie is dependent on IP address. The logic is simple. If we want to prove the dependency between the cookie and the feature, what we can do is change the value of the feature and check whether the cookie is changing as well. To add certainty, we can set the feature to its initial value and check if the cookie is back to initial value. We spoke the IP address that is pointed to a different location, and we visited the bbc.com website several times. We mark in a red cross the visits where we detect that the value of the cookie 1234 changed. Otherwise, we mark it in a gray cross, and we repeated that several times. Similarly, we set the IP address to initial value and check if the cookie is set to its initial value, 1234. If it's the case, we mark it in a gray plus. Otherwise, we mark the website visit as a red cross. And we repeated that several times again. Next, we performed a statistical test, permutation test, and we considered that the cookie is IP dependent if it's statistically significant. As a result of this study, we detected 1,425 cookies that are respond using at least one of the studied features. I have to mention that in our work, we considered 8 fingerprinting features. You can always refer to the paper for more details. We found that these cookies appear on 1,105 visited websites. Now, I'll present part of our result on what features are used for responding, on what categories of websites we detect such behavior, and what are the tracking and legal consequences of cookie responding with browser fingerprinting. Among the 8 studied fingerprinting features, we found that the IP address is the top feature used to respond cookies. In fact, 25% of cookies are responded using IP address alone. We categorized the websites where we detected responding, and we found that responding is happening on over 140 different categories. News websites is the top category of websites, including cookie responding. In fact, among the visited websites, 5.95% of news websites contained at least one response cookies. Finally, we found that responding is also happening on sensitive websites such as adult websites. We detected 21 cookie instances that are respond on such websites. As we mentioned earlier, browsers are moving toward the deprecation of third-party cookies. However, we found that cookie responding with browser fingerprinting can enable persistent cross-site tracking even after the removal of third-party cookies. Let's consider this example. The user is visiting bbc.com that includes a fingerprinting script from adinaccess.com. A request is sent to adinaccess along with the browser and machine features. Adinaccess extracts the fingerprint, FP456, and store it on a matching table with a corresponding identifier 1234. Then it will send back the ID to adinaccess script that will store the ID in a first-party cookie. Next, let's say that the user visits newyorktimes.com that includes a script from the adinaccess. So once again, a request is sent to adinaccess with the browser and machine features. Adinaccess checks the matching table, extract the corresponding identifier 1234. The script running in the context of newyorktimes.com will store a second first-party cookie with the ID 1234. As a result, on the user's browser, we will have 2 first-party cookies set by adinaccess with different hosts and same value. Using these cookies, adinaccess can ensure persistent cross-site tracking without relying on third-party cookies. We detected 40 respond first-party cookies instances that are set by same domain on different websites and share the same value. These cookies can serve for cross-site tracking. With the help of a legal scholar, we evaluated the legal consequences of cookie responding with browser fingerprinting. We found that cookie responding violates a number of principles. First, fairness principle. The fairness principle mandates that personal data must be processed fairly. That is, we should not have any surprising effects. The recreation of cookies after being removed is indeed a surprising effect for users. Therefore, all 1,425 response cookies are violating the fairness principle. Next, we evaluated the transparency principle that mandates that personal data processing must be handled in a transparent manner. We analyzed the top 10 popular response cookies owners' policies, and we found that none of them is actually mentioning the usage of cookie responding. Finally, we found that cookie responding with browser fingerprinting violates the lawfulness principle. The lawfulness principle mandates that websites should obtain users' consent. I have to mention that in our study we never consent to cookies. However, not all cookies are subject to consent. To evaluate whether a cookie is violating the lawfulness principle or not, we extracted the purposes of response cookies, and we found that 38.69% of the response cookies are indeed subject to consent and therefore violating the lawfulness principle. As we mentioned earlier, not all cookies are subject to consent. In fact, there is three criteria used to evaluate whether a cookie is exempted or subject to consent: the purpose of the cookie, the duration, whether it's a session or persistent cookie, and finally the context, whether it's a first or third-party cookie. We found that cookie spawning with browser fingerprinting can actually bypass the criteria used to identify the need of users' consent. In fact, 31.30% of the response cookies are session cookies. These cookies can be exempted from consent because of their duration, the fact that they are session cookies. However, because of the usage of cookie spawning with browser fingerprinting, these cookies are used in a persistent way. To conclude, in this work, we designed a methodology that helps identify which features are used to respond cookies. We performed the first study on cookie spawning with browser fingerprinting, and we showed that this tracking technique overcomes the duplication of third-party cookies and ensures persistent cross-site tracking. Finally, we performed a legal analysis and showed that cookie spawning with browser fingerprinting violates the GDPR e-privacy directive. Thank you for your attention.